Now wait a minute. Here's something that ought to bother you. Why can't you go faster than light? I mean, really, who says? If I'm in a car going 60 miles an hour and I step on the gas, I go 70. I step on it harder, I go 80. What's stopping me from just, keeping my foot down until I'm going faster than light? Is there some cosmic policeman out there with a badge that says 186,000 miles per second, not 1 mile more? The answer is stranger than any policeman. The answer is that the universe itself is built in such a way that the question doesn't even make sense. And by the time we're done here today, you're going to understand why. Not just accept it because some professor told you. You're going to see it. You're going to feel it in your bones. And I promise you, the way the universe actually works is far more interesting than any science fiction story about warp drives. Let me start with something ordinary, something you do every day without thinking about it. You're sitting on a train, a nice smooth train, no bumps, curtains drawn, you can't see outside. Now I ask you, are you moving? Well, you might say, I don't know, let me look out the window. But I said the curtains are drawn, so you try something clever. You take a ball out of your pocket and you toss it straight up. It comes straight back down into your hand. Does that tell you if you're moving? No! It doesn't! Because whether that train is sitting still at the station or gliding along at 60 miles an hour on perfectly smooth tracks, that ball behaves exactly the same way. You toss it up, it comes down. No difference. This bothered people for a long time. Galileo thought about this kind of thing. Newton thought about it. They realized something profound. There is no experiment you can do, locked inside that train, that will tell you your absolute speed. You can only measure your speed relative to something else. The platform, another train, the trees going by. But absolute speed has no meaning. Now hold that thought, because I'm going to add something that changes everything. Along comes a fellow named Maxwell, James Clerk Maxwell. He writes down the equations for electricity and magnetism, and buried in those equations is a speed, the speed at which electromagnetic waves travel, light waves. And that speed comes out to be about 186,000 miles per second. Now here's the funny thing. The equations don't say 186,000 miles per second relative to what? They just say 186,000 miles per second, period. This is very strange. If I throw a baseball at 50 miles per hour from a car going 60 miles per hour, someone standing on the sidewalk sees that ball going 110 miles per hour. You just add the speeds. That's common sense. That's what Galileo would tell you. So suppose I'm on that train going half the speed of light, and I turn on a flashlight pointed forward. The light leaves my flashlight at the speed of light. So someone on the platform should see that light going 1.5 times the speed of light, right? Half plus 1 equals 1.5. Wrong. Dead wrong. And this is where everything gets interesting. When we actually do the experiment, and you can do this experiment very precisely with modern equipment, you find that the person on the platform measures that light going at exactly the speed of light. Not 1.5 times, just the speed of light, the same 186,000 miles per second. And it's not just that one experiment. You can do it 1,000 different ways. You can be moving toward a light source, away from it, sideways, spinning in circles. It doesn't matter. You always measure light going at the same speed. Now wait, think about what that means. If you and I are moving relative to each other, and we both measure the same beam of light, we both get the same answer for how fast it's going. That's like two people measuring the same car with different rulers and somehow getting the same number even though their rulers are different lengths. It sounds impossible. Einstein grabbed hold of this impossibility and said, all right, if this is what nature is telling us, let's take it seriously. Let's assume that the speed of light is the same for everybody, no matter how they're moving. And let's see what the consequences are. This is the key move. This is where the magic happens. Instead of saying, that's ridiculous, there must be something wrong with the experiments, Einstein said the experiments are right. I must be wrong about something else. And what he found was that the something else was our ordinary, everyday notions about space and time. Let me show you what I mean. I'm going to take you through a little thought experiment. Imagine I build a very simple clock, the simplest clock you can imagine. It's just two mirrors facing each other, and a single pulse of light bouncing back and forth between them. Every time the light hits the bottom mirror, we call that a tick. Up, down, tick. Up, down, tick. Very simple. Now I put this clock on a train. The train goes by you at some tremendous speed, let's say half the speed of light. You're standing on the platform watching. From my point of view, sitting on the train, the light goes straight up and straight down. Simple. The distance the light travels is just the distance between the mirrors. Let's call it 1 foot. Up 1 foot, down 1 foot, tick. But what do you see standing on the platform? You see the train moving sideways while the light is going up and down. So from your point of view, that light is not going straight up and down. It's going diagonally. It goes up and to the right, then down and to the right, like a zigzag. Now here's the key. What's the speed of that light from your point of view? It's still the speed of light. We said that's the rule. Everyone measures light at the same speed. But wait, the path is longer. The diagonal path is longer than the straight up and down path. If the light is going the same speed but traveling a longer distance, what does that mean? It means it takes longer. From your point of view, my clock is running slow. Now you might say, but that's just an optical illusion. That's just how it looks to you. The clock is really running at the right speed. But no, that's not how it works. This isn't about appearances. This is real. If I travel away from you at high speed for what my clock says is 1 year, and then I come back, I will have aged less than you. My heart will have beat fewer times. I will have thought fewer thoughts. Everything about me, every physical process, runs slower when I'm moving relative to you. This is called time dilation. And it's not a theory anymore. We've tested it with atomic clocks on airplanes. We've tested it with particles and accelerators. It happens. It's real. Now let me check that I'm being clear here. Let me explain this as if I'm talking to a bright young kid who's never heard any of this before. Here's the deal. Light always travels at the same speed, no matter who's watching. But speed is just distance divided by time. So if the speed is fixed, but the distance looks different to different people, something else has to change to keep the equation balanced. That something else is time. When you're moving fast relative to me, your time runs slower from my point of view. Not because your clock is broken, not because there's something wrong with you, but because that's how the universe works. Time itself is flexible. It stretches and squeezes depending on how you're moving. And here's the really mind-bending part. From your point of view, you're standing still and I'm the one who's moving. So from your point of view, my clock is the one running slow. We each think the other one's clock is slow. And we're both right. But that's contradictory, you say. How can we both be right? It seems contradictory because you're imagining that there's some absolute universal time, some cosmic clock in the sky that tells you what time it really is. There isn't. There's just your time and my time, and they're not the same when we're moving relative to each other. Now I want to talk about a misconception that almost everybody has. Almost everybody who hears about this thinks they understand it, and they're wrong. The misconception is this: nothing can go faster than light. You hear that and you think, okay, 186,000 miles per second is the speed limit. Just like the speed limit on the highway. You can go up to that speed but not past it. But that's not quite right. The real statement is more subtle, and it's more interesting. The real statement is, if you're moving slower than light, you cannot accelerate to the speed of light or beyond. And if you're already moving faster than light, you cannot slow down to the speed of light or below. Now, wait. Does that second part mean there might be things already going faster than light? Well, we've never seen one. These hypothetical particles are called tachyons. They would have very strange properties. They would have what we call imaginary mass, which is a mathematical curiosity. And they would violate causality, which means they could carry effects backward in time. Most physicists think tachyons don't exist, but the mathematics doesn't absolutely forbid them. It just says they could never slow down to light speed. But here's the real reason you can't speed up to the speed of light. As you go faster and faster, getting closer and closer to the speed of light, something happens to your mass. And by mass, I mean your inertia, your resistance to being pushed. You know how when you push a shopping cart, it accelerates? The harder you push, the faster it speeds up. Well, as things get faster and faster, approaching the speed of light, they become harder and harder to push. They resist acceleration more and more. Think of it like trying to push a car uphill. At first, it's hard but doable. But as you go up, the hill gets steeper and steeper and steeper. And as you approach the speed of light, it's like the hill becomes vertical. You could push with all the force in the universe, and you'd barely budge it. In fact, to accelerate a massive object all the way to the speed of light would take infinite energy. And we don't have infinite energy. Nobody has infinite energy. So you simply can't get there. Now, why is this? What's really going on? Let me try another way of looking at it. Einstein showed that energy and mass are related. This is where that famous equation comes from. E equals mc squared. Energy equals mass times the speed of light squared. What this tells us is that mass is really just a form of energy, and energy is really just a form of mass. When you speed up an object, you're giving it energy, kinetic energy, the energy of motion. But if energy is mass, then you're also giving it mass. The faster it goes, the more energy it has, and the more mass it has. And the more mass it has, the harder it is to make it go faster. It's like trying to catch up to someone in a race, but every step you take, the finish line gets farther away. Every bit of energy you put in makes the object more massive, which means you need even more energy to speed it up, which makes it even more massive. Now, some people don't like this way of talking about it. They say, the mass isn't really increasing. It's just the relativistic momentum that's increasing. And technically, that's a more careful way to say it. In modern physics, we usually talk about rest mass, which is the mass of an object when it's sitting still. And that doesn't change. What changes is how the object responds to forces when it's moving fast. But the effect is the same. The faster you go, the harder it is to go faster. Let me give you a different way to see why light speed is special. This one's a bit more abstract, but it's very beautiful. Imagine you're driving north. You're going 60 miles per hour north. Now imagine you turn your steering wheel a little bit to the right. Now you're going a little bit north and a little bit east. What happens to your northward speed? It decreases, right? Because some of your total speed is now going eastward instead of northward. Your total speed is still 60 miles per hour, but it's split up between two directions. You can't go 60 miles per hour north and 60 miles per hour east at the same time. Not if your total speed is limited to 60. Now, here's the weird thing. According to relativity, everything is always moving through space-time at the speed of light. Always. Everything. You, me, that table, the planet, all of it. Wait, you say. I'm sitting still. I'm not moving at all. Ah, but you're thinking about motion through space. What about motion through time? See, space-time has 4 dimensions, 3 of space and 1 of time. And in this 4-dimensional picture, everything is always moving at the speed of light through space-time. When you're sitting still in space, all of your motion through space-time is going into the time direction. You're moving through time at full speed, but when you start moving through space, some of your space-time velocity has to go into the space direction. And just like with the car, that means less goes into the time direction. The faster you move through space, the slower you move through time. And if you could move through space at the full speed of light, then none of your space-time velocity would be left over for the time direction. You'd be moving through space at light speed and through time at 0 speed. Time would stop for you. This is exactly what happens to light. Photons, the particles of light, travel at the speed of light through space, and they don't experience time at all. From the perspective of a photon, the instant it's emitted and the instant it's absorbed are the same instant, even if a photon travels from a distant galaxy for 1 billion years by our clocks. From the photon's perspective, no time passes whatsoever. Now, that's remarkable. And it tells you something deep about the nature of light. Light doesn't have rest mass. It never sits still. It can't. If it ever stopped moving through space, where would its motion through space-time go? Photons are locked into moving at exactly the speed of light. Not faster, not slower, always exactly c. Things with mass, like you and me, are locked into moving slower than light through space. We can move through space at any speed, from 0 up to just under the speed of light, but never at light speed or above. Why? Because to move through space at the speed of light, we'd have to give up all our motion through time. We have to stop experiencing time altogether. But things with mass can't do that. We're fundamentally different from photons in that way. This is one of the deepest asymmetries in physics. Massless things must travel at exactly c. Massive things must travel at less than c. The speed of light isn't just a speed limit. It's a boundary between two fundamentally different kinds of existence. Let me take you through one more thought experiment. This one really shows why breaking the light barrier would be catastrophic for our understanding of the universe. Suppose you could send a message faster than light. Let's say you have a magic telephone that transmits instantly, no delay at all. You're on Earth. I'm on a spaceship heading away from you at high speed. I call you on the magic telephone. At the moment I call, according to my clock, it's noon on Tuesday. You receive the call instantly. But here's the thing. Because we're in relative motion, our clocks are out of sync. According to your clock, when you receive my call, it's 1:1 a.m. on Tuesday. You immediately call me back, also using the magic telephone. Instant transmission. I receive your call. But again, because of our relative motion, our clocks are out of sync in the opposite direction. According to my clock, when I receive your call, it's 1:0 a.m. on Tuesday. Now wait. I sent my call at noon. You received it at 11 a.m. You sent your reply. I received it at 10 a.m. I received your reply 2 hours before I sent my original message. This is a time travel paradox. Information has traveled backward in time. I could receive a message telling me what I was about to say before I said it. I could decide not to say it. Then where did the message come from? This isn't just a weird quirk. It's a fundamental violation of causality. Effects would happen before their causes. The universe as we understand it would become self-contradictory and nonsensical. The speed of light isn't just a speed limit. It's the speed of causality. It's the fastest that any influence, any information, any effect can propagate through the universe. And this is why, in relativity, if two events are connected by something traveling slower than light, all observers agree on which event happened first. They might disagree about how much time passed, but they agree on the order. But if two events were connected by something traveling faster than light, observers in different states of motion would disagree about which event happened first. Some would say A caused B, others would say B caused A, and that would make cause and effect meaningless. The universe doesn't allow that. The speed of light protects causality. Now, I want to be careful here. I've been talking as if all this is absolutely certain, and for the physics we know, it is. But we should always have some humility. Physics is an experimental science. We believe things because experiments confirm them. Is it possible that someday we'll find something that breaks these rules? Well, we can't rule it out absolutely. Science is always provisional. But the experiments we've done, and they are many, and they are precise, all confirm that the speed of light is the universal speed limit. Some people ask about things like quantum entanglement. You might have heard that entangled particles seem to affect each other instantly, even when they're far apart. Does that violate what I've been telling you? No, it doesn't. And this is subtle, so let me be careful. In quantum mechanics, you can have two particles that are correlated in a strange way. If you measure one and find it spinning clockwise, the other one will be spinning counterclockwise, no matter how far apart they are. And this correlation exists instantly, in some sense. But here's the key. You can't use this to send a message. The outcomes of the measurements are random. You can't control what result you get. You can only see, after the fact, that the results were correlated. The correlation is real, but there's no information transfer, no causality violation, no paradox. Physicists argue about what this really means. There are different interpretations. Some say there's some kind of faster than light influence, but it's not information, so it's okay. Others say there's nothing actually traveling anywhere. It's just that the particles were always correlated from the start. We don't fully understand quantum mechanics, that's honest. But whatever's going on, it doesn't let you send messages faster than light, and it doesn't violate causality. Let me zoom out now and talk about what all this means for how we see the universe. Before Einstein, people thought of space and time as a stage. Fixed, absolute, unchanging. Events happened on this stage, but the stage itself just sat there. Space was space, time was time, and they had nothing to do with each other. Einstein showed that space and time are woven together into a single fabric called space-time. And this fabric isn't fixed. It's dynamic. It can stretch and squeeze. It curves in the presence of mass and energy. The speed of light is the key that unlocks all of this. It's the conversion factor between space and time. It tells us how much time is equivalent to how much space. And it's built into the very structure of the universe. When we talk about distances in astronomy, we often use light years. The distance light travels in a year. That's not just a convenient unit. It's telling us something deep about how space and time are related. If a star is 10 light years away, that means the light from that star takes 10 years to reach us. When we look at that star, we're seeing it as it was 10 years ago. We're looking back in time. The farther we look in space, the farther we look back in time. The edge of the observable universe is about 46 billion light years away, and the light from there has been traveling since nearly the beginning of time. Looking out in space is the same as looking back in time. This is why the speed of light matters so much. It connects space and time. It tells us that the universe has a structure where cause and effect can propagate, but only so fast. It tells us that information takes time to travel, and that now in a distant place is not a meaningful concept. There is no universal now. There's only the past light cone and the future light cone. The past light cone is everything that could have influenced you. The future light cone is everything you could possibly influence. Everything else is causally disconnected from you, at least right now. This changes everything about how we think about reality. We don't live in a universe of absolute space and time, where everything happens on a fixed stage and light is just something that travels across it. We live in a universe of space-time, where light speed is the fundamental constant that ties everything together. And you know what's beautiful about this? It's that we can understand it. The universe is strange, but it's not arbitrary. The rules make sense. They fit together. Once you accept that the speed of light is the same for everyone, all the rest follows logically. Time dilation, length contraction, the impossibility of faster-than-light travel. It all hangs together. Einstein didn't invent these rules. He discovered them. They were there all along, built into the fabric of reality. Nature is telling us something, if we're willing to listen. Now, some of you might be feeling a bit unsettled. This is a lot to take in. The idea that time is flexible, that there's no universal now, that you can never go faster than light. It goes against everything our everyday experience tells us. But remember, our everyday experience is limited to very slow speeds and very weak gravity. We're like fish who've never left the pond. Of course, the ocean seems strange to us, but it's not strange. It's just bigger than what we're used to. And here's the amazing thing. We can still figure it out. We can't travel close to the speed of light ourselves. Not yet, anyway. But we can do experiments. We can watch particles that do travel that fast. We can measure atomic clocks with incredible precision. And everything confirms what Einstein said. The universe is stranger than we thought, but it's not unknowable. We can understand it. That's the great adventure of physics. Let me tell you one more thing before I let you go. Something that ties this all together. Why is the speed of light what it is? Why 186,000 miles per second and not some other number? Honestly, we don't know. It's one of the fundamental constants of nature. It just is what it is. We can measure it, but we can't explain why it has that particular value. Some people find that unsatisfying. They want a deeper reason, and maybe someday we'll find one. Maybe there's some deeper theory, some more fundamental level where the speed of light is derived from something else. But maybe not. Maybe some things just are. Maybe the speed of light is one of the inputs to the universe, not an output. The rules of the game, not a consequence of the rules. What we do know is that if the speed of light were different, everything would be different. Chemistry would work differently. Stars would burn differently. Life, if it could exist at all, would be utterly alien. We live in a universe tuned, somehow, to allow complexity and life. The speed of light is part of that tuning. Whether that's an accident, or design, or one of infinitely many universes with different constants, we don't know. That's another question, a big one. But here's what we can say. The speed of light is the cosmic speed limit because space and time are woven together, and that's how the weaving works. The speed of light is the same for everyone because the laws of physics are the same for everyone. And the speed of light is finite, not infinite, because the universe has structure. Cause and effect need time to propagate. Nothing happens everywhere at once. The universe is not a collection of isolated points connected by invisible, instant threads. It's a fabric where everything is connected, but the connections take time. The speed of light tells us how much time. And that's beautiful. It means the universe has a story. Things happen in order. Effects follow causes. There's a past and a future, and they're different. If everything could happen instantly, everywhere, there would be no story, no time, no change, no us. So thank the speed of light. It makes causality possible. It makes time possible. It makes the universe possible. Now look, I've talked your ear off. I hope some of this made sense. I hope I've given you something to think about, some new way to see the universe you live in. Because that's what physics is for. Not to make you memorize equations, not to pass tests, but to see, to really see how nature works down at the deepest level, to understand the rules of the game. And the universe is playing a wonderful game. The rules are strange, but they're not random. They fit together like a beautiful puzzle. And we, somehow, are able to figure them out. That's the miracle. That's the joy of it. So go think about this. Go look at a beam of light and remember what you've learned today. Remember that that light is always traveling at exactly the same speed, no matter how you're moving. Remember that your time and someone else's time are not the same, that space and time are woven together, that the speed of light is the thread that holds it all. And if you want to go faster than light, sorry, can't do it. The universe says no. But don't be disappointed. The universe is saying something much more interesting than no. It's saying, let me show you how things really work. And that's worth more than any warp drive. Now, I'd love to hear from you. After all this, what's the one thing that still puzzles you? What's the part of this that doesn't quite sit right? Write it down. Post it in the comments. Let's keep thinking about this together. Because that's how physics works. One question leads to another, and before you know it, you've understood something you never thought you could. That's the best feeling there is.